Here are the outlines of our lecture. First, it will be the objectives and the learning outcomes. Then I will present to you a nutshell of the Newton-Raphson method, followed by an example. After that is a home assignment, and finally some remarks. The first objectives of our lecture is to provide you with a numerical solution of equation using the Newton-Raphson iteration procedure. The second objective is to demonstrate how to solve petroleum engineering related equations using the Newton-Raphson method. For the learning outcomes, I hope you'll be able to formulate a solution of the equation using the Newton-Raphson method, and you'll be able to construct the solution of the petroleum engineering related equation using the Newton-Raphson method that you learned in this lecture. The Newton-Raphson method, or the Newton's method, named after Sir Isaac Newton and Joseph Robson, is the iteration method to find the root of equation fx equals 0. You already know that to find a root of equation, we can substitute any value of x into the equation until fx equals 0. For example, fx equals x cubed plus 3x subtract 5 equal to 0. You can do a first try by substituting x equal to 0 into the equation. You obtain fx equals negative 5. This just means that x equal to 0 is not a solution. For the next trial, you can try a different value of x. But if you keep doing this, it will be very time consuming because you don't know which direction you should go. Then Newton-Raphson will offer you the way of selecting the next value of x based on the value of x that you used before. If I denote xi as the ith guess of x, we want to select the value of delta xi so that fx plus delta x equals 0. From Taylor approximation, we know that fx plus delta x will be equal to fx plus delta x times df over dx. Because you want to have fx plus delta x equal to 0, so this term has to be equal to 0. So you set this one equal to 0 and you obtain the value of delta x from this equation. This is exactly the core of the Newton-Raphson method. For example, to solve the equation x cubed plus 3x subtract 5 equal to 0, as we have before, we can try a value of x equal to 0, and then you obtain fx equals negative 5, and df over dx equal 3. So for the next trial, Newton-Raphson said that you have to use x equal to 5 over 3. Then if you substitute this value into the equation, you will obtain a value of fx and a value of df over dx, and you keep repeating this procedure, you will hopefully obtain the solution. To do that, I already construct an Excel spreadsheet, a table here, to obtain the solution. So for the first step, we already calculated this value, and the next value of x will be equal to the previous one plus delta x. We obtain it and put it here, and you calculate the value of f and df over dx, and using the Newton-Raphson formula to obtain delta x at step 1. Then if you keep doing this, it will to the 6th step will finally obtain the solution. And our solution is x equals 1.155. So the procedure for the Newton-Raphson method is the first step you make an initial guess of x0, in this case I equal to 0, and you calculate f xi and df over dx, and you use the Newton-Raphson recommendation to obtain delta x at step I, and you check for conversion. If delta xi is smaller than epsilon is tolerated, then you end iteration because you already reached the solution. If it is not smaller than epsilon, then you calculate the value of x at step I plus 1 equal to x at step I plus delta xi from this equation here. Then for this one, you have to count the number of steps as well. Now the fourth step, you check if the number of steps that you have tried is larger than the maximum step, then you need to end the iteration. Otherwise, the code will be run forever, and it will never reach the solution. In this case, you can go back to step 1 and you try a new value of initial guess. If it had not reached the solution yet, reach the maximum step yet, you can try a new value. You assign the value of xi equal to xi plus 1, and you go to step 2, and you do this again until you get the conversion. Now, for an example, I provide a procedure to calculate the pressure gradient of a Power fluid flow in a drill pipe as the following. The pressure gradient is obtained from this equation. dP over dz equal to 2 over the pipe radius times tau. Tau is the shear stress at the wall of the pipe, and it can be calculated from the constitutive equation for the Power law fluids like this. And we have equation to coordinate the velocity, the average velocity, with the rheological properties of the fluids and the wound shear rate. Look at this equation here. You see that the first thing you need to find the value of wound shear rate from this equation by a numerical method or any method to obtain the wound shear rate, and from wound shear rate you can obtain the wound shear stress, and from wound shear stress you can obtain the pressure gradient, which is the pressure loss when the fluid flow along the drilling pipe in 1 unit length. The pressure loss in 1 unit length when the drilling fluid flows to a drilling pipe. Here tau y is the yield stress, n is the flow consistency index, k is flow behavior index. In example, I have a drilling fluid with tau y equal to 8 Pascal, n equal to 0.6, k equal to 0.3, and average flow rate is 1 meter per second. And I ask you to estimate how much the friction pressure loss when the fluid is flowing along 1 meter of the drill pipe. This one we call it the frictional pressure gradient. So basically, the idea of this problem is you need to find the value of wound shear rate from this equation. Because this equation is nonlinear and very challenging to solve it analytically. So you have to find the solution using the Newton-Raphson method that I teach you in this class. Now to do this, first you need to set a function f equal to this one, and here I set the value. I write this one in a short formula by setting this equal to a here, and this one in the brackets equal to b here. Then it equal to a times b subtract the average velocity. We also obtain df over d1 shear rate from this equation. You take the derivative analytically, and I also set this one equal to c, and this one already equal to b equals b already here, and this one is I set it equal to this one already equal to a, and this one equal to d here. The main reason I'm setting this coefficient is so that the equation will make it simpler and easy to write the spreadsheet for it. Now let me go to the spreadsheet and show you how to do this. Now I have this is input. Let me put this one at an input. This one is the pi radius. I already call it RP here, RP, and this one is flow consistency index. I name it K underscore your power law, and this one is the flow behavior index. I call it N underscore your power law. Same thing, this one is tau, which is the yield stress, and this one is V is flow velocity. Now I construct a table here to solve this problem. First of all, I need to have step so that I check how many steps it will be converged. Now the first step, I call it step 0. This column will be X. This is A, B, C, D, F, X, df over dx, and this one will be delta x, and this one I check for conversion. Now the first guess, I get the value of x equal to 100. Now I need to write a formula for a, right? To save the time, I already prepare the formula for a here. A equal to this one. I put it here. To save the time, you can do it at home if you prefer to rewrite it. Now a equal to that one, and b, this formula, so b equal to this one. Now I put an equal sign here. Next, I need to have value of c equal to this one. I copy it again and I put it here. Oops. Now hit enter. It's okay. I will make this one do the same format as this one. Now here you go. C. Next, D. You can when you are at home, you can rewrite this formula by yourself so that you know how to construct it. Equal this one and hit enter. Now F will be equal to A times A times B, and you have to subtract you have to subtract the flow velocity, hit enter, and df will be equal to b times c plus a times d. Now we have delta x will be equal to negative f over df. Good. So the next step will be step 1. Let me put a step here. Up to 25 steps and see how it look like. It'll be equal to this one, the x0 plus this. Hit enter. Then you calculate a new value of a, b, c, and df over dx. So you just drag this down. Actually, you can drag it to 25 steps. Then you drag this one down to here. Then you need to check if it converges or not. And I set an if function here to check whether it's converges or not. If ABS is the stand for absolute, so I check the absolute value of this one. If this one is smaller than, let me put this one. Let me first write the tolerancing here. Tolerancing or epsilon. Tolerancing equal to 1 e to the power of equal to 1 e to the power of negative 6. Now I call this one epsilon. Now let me write this if function again. If ABS delta x smaller than epsilon, yep. Then I say yes, it converges. Else I say no. Oh, so the first step is not converge yet. Let's do it for the next step. Then you can see that after about 20 trials, you obtain the solution. And here is the solution. Now, so I write here this one shear rate, and make it bigger, equal this one. Put the number here, hit enter. So the wall shear stress can be calculated by using the constitutive equation, right? Wall shear stress, make it bigger, equal to yield stress plus k u power law underscore u power law times shear rate to the power of n underscore u power law. Oh, that is the one shear stress. So the pressure gradient equal to 2 over Rp times tau wall, 2 over Rp here times tau wall, which is tau, not tau wall. Tau wall is this one, the one that we just calculated. This one is the unit of this one is 1 over second, and the unit of this one is Pascal. So the unit of this one will be Pascal over meter. And here is our solution. So we already obtained the solution of more than 557 Pascal per meter. That is the pressure gradient. Then I can put the solution here. Oops. I put the solution here. Solution is, it's okay. I put the solution here. Make it bigger so you can see it, and you can use it for the next method that we are going to learn soon. Now for the home assignment, I assign you a similar problem, but in this problem you need to write a computer code. I already teach you how to use VBA in this course, so you should be able to write a VBA code to solve the same problem. And you can compare the result with the result you obtain from the spreadsheet. In summary, in this lecture, I already provide you a formulation of the Newton-Raphson iteration procedure to find a root of equation. This one is not a perfect method to find any to find the root of any equations, but it's very effective method that we use a lot in petroleum engineering. If this one doesn't work, then you can try different method using the method that I already teach you in this course. For example, the bisection method. And the next lecture I will teach you how to use the second method. And you already know how to formulate the procedure to find the root of equation using the Newton-Raphson method. And you can use Excel to find root of equations using the Newton-Raphson method. If you have any question, you can put it in the comment.